In this latest video in our series on doing things with geometric algebra, we will use the concept of rejections of one vector with respect to another in order to find the radius and the center of a circle that is inscribed within a given triangle. And this problem is worked out in more detail in a document that's been uploaded to Vixra, and I will link that document in the video description. So some of the ideas that we will use in this video are that a line that is tangent to a circle, for example, the line of a side of a triangle, is perpendicular to the radius that is drawn to the point of tangency, which we have 3 of them here. Also, something we've seen in previous videos, for any 2 vectors rather, u and v, the magnitude of the outer product of those vectors is equal to twice the area of the triangle that is formed by those vectors. So here is our triangle that is formed by the vectors u and v, and the magnitude of u wedge v is a scalar that is equal to 2 times the area. And here we'll look a little bit more at the idea of the rejection of a vector, and I'll move on to the next slide so we can see this more clearly. So the notation here is rejection of the vector v with respect to the vector u. So formally, and Heston and other sources go into this and do a nice job explaining it, the rejection of v with respect to u is v wedge u, or outer product of v with u, times the multiplicative inverse of u. And now we can do some things here to get to get a different idea at least of what's going on that may help us out on this problem and on others. So let's look at this a bit. The multiplicative inverse of u is a vector u divided by the square of u's magnitude, or u squared here. So now let's distribute u squared down here and look at it a bit more. The vector u divided by its own magnitude is the unit vector u. So now we have v wedge u divided by the magnitude of u. And if we look at this, the outer product of v and u is some scalar multiple of the unit vector, or of the unit bivector I, for the plane that contains v and u. So we can always write this v wedge u as some scalar multiple of that unit vector I. But what scalar multiple is that? Well, it's either going to be the positive or negative of the magnitude of v wedge u divided by u. So why is it either positive or negative? Well, if the rotation of u from u to v is in the same direction of rotation of I, then it will be positive. And if it's in the contrary direction, it'll be negative. So let's move on here a bit. Geometric algebra is an associative algebra, so instead of associating I with the scalar, we'll associate I with the vector here. And we'll reverse sign here, or we'll reverse the order here. If we reverse the order of this product I times u, we change the sign. So where we had plus or minus, now we have minus or plus. So the rejection v here will be this scalar times u hat I. So we can see that the rejection and u hat I are in the same direction. But what really interests us in this problem is the magnitude of that rejection. So here we have a scalar times a unit vector. And what is the magnitude of a scalar times a unit vector? Well, it's the scalar. So the rejection, or the magnitude of the rejection here, is the magnitude of the wedge product divided by u. And let's look at that just a little bit more here, because we want to understand kind of a geometric interpretation. We've seen in previous videos, and in fact mentioned earlier here, that v wedge u is twice the area of the triangle that in this case would be formed by u and v. So that rejection, or the magnitude of that rejection, is 2 times the area of that triangle divided by u. And if we look at it here, just kind of to make it more coherent and give us another idea of what's going on and be more comfortable with it, what do we have here? Well, v wedge u is twice the area of this parallelogram, and we're dividing it by the length of the base, which is u. So all we have here is that the height of that parallelogram is the area of the parallelogram divided by its base, something we've all known basically forever. So all that checks out and makes sense, and maybe now we're a little more comfortable just going ahead with this. So let's explore this problem that we have here of finding the center and radius of the inscribed circle. Two of the features that we can make use of, we hope, are that the center has to lie along, or has to be at the intersection of the bisectors of the vertex angles. Another feature is that the center, of course, has to be equidistant from the three sides, and that distance is r, the radius of the circle. Now, I'll go back one step here. We could use the idea that that center is at the intersection of these bisectors. And I did the problem that way, and it turned out to be fairly nasty and not very insightful. So I decided to go ahead and solve it using the rejections, and I hope that will be of benefit to the viewers. So our strategy will be to use rejections and to find the point along this bisector at which the distance from side A, side B, and from side C is the same. So we formulate the problem in this way. Again, that point has to lie along a line that is equidistant from the sides A and B, so that vector to that point has to be some scalar multiple, I've called it gamma, times the vector A hat plus B hat. And also, here's a kind of a summary of what's going on here. The distance A is the magnitude of the vector A and so on here, and the vector Z from the origin to that point is some scalar multiple of A hat plus B hat. And again, in the document that's uploaded to Vixtra, this is explained a little better if you want to consult that. So let's get on with the solution here. What we're going to do, we have two unknowns, r and gamma, so we're going to develop two equations. The first equation expresses the equidistance of this point from the sides A and B. So in order for this point to be equidistant from the two sides, it must be at the distance r from side A, or also from side B. We could work it that way, but using it as a rejection with respect to A of Z, which is gamma times A hat plus B hat, and then expressing that as the wedge product, well, A hat wedge A is 0, so we just get B hat wedge A, and when the smoke clears and we do a few other things, we get our first equation that relates gamma and r. Gamma is A times B times r over 2 times A. The second equation, well, here we make use of the fact that a vector does not possess the attribute of location. So to see better what's going on, we don't use this side here. We find the rejections with respect to B minus A by drawing the vector down here, and that makes everything clearer. Because what we want is a rejection of A with respect to B minus A, and the rejection of Z with respect to B minus A. So we can see here that the distance r is equal to the rejection of A itself minus the rejection of Z. And I've written that formally down here, and when we play around with this and the smoke clears, this is what we get. R is equal to, well, you can read it yourself. Now, there's an important little maneuver in some of these simplifications, and again, it's explained a little bit more and called out more clearly in the document itself that I uploaded. Here, when we wedge A hat with A, that drops out, so we're just left with B hat wedge A. B hat wedge A is not of any use to us as it is. So we multiply top and bottom here, or numerator and denominator, by the magnitude of b, so that instead of having b hat wedge a, we have b wedge a, which is 2 times the area. So that's an important little detail in the math there. And this because of equation 6.1, well, that's a reference to an equation that's in the document that's uploaded. So when we're all done here, what we get is, well, you can read them yourselves. The radius is this, and the location of the center with respect to this origin here is, well, it's that. Now a little finesse that we can do here, and again this is an extract from the document that was uploaded to Vixra. By Heron's formula, the area of a triangle is equal to this product here where S is the semi-perimeter, the sum, half the sum of the sides. But because in this formula here, the denominator of the expression for r is a plus b plus c, we can simplify this kind of nicely, and we end up with r is equal to s minus a times s minus b times s minus c over s. So it's just kind of a nice little detail that comes out of it. So again, the document that explains this more fully is at Vixra, and I will link that in the video description. And I hope you'll also consider joining our LinkedIn group, or our associated LinkedIn group, and I'll link that also in the video description. I hope this video has been helpful. I look forward to your comments and improvements on this solution, and thank you for your time.